So to start, imagine building a bridge and the measurements on one end don't match the other, or launching a satellite only to find its position data contradicts itself. In a world where precision can mean the difference between a structure that stands and one that fails, accuracy in measurement is everything. That's where 3D geodetic network adjustment comes in. Every time we collect distances, angles, or GNSS data in the field, we don't get perfect numbers. We get approximations, each with its own small errors left uncorrected. These errors stack up. They contradict each other. They create a picture of the world that is almost right. But almost right is never good enough in geodesy. So what's the solution? We don't just correct one measurement. We correct all of them simultaneously. Using the power of mathematics to find the single best fitting solution across the entire network, that process is called 3D geodetic network adjustment, and it is the backbone of reliable geospatial data. Today, our group will walk you through exactly how this works, from the raw inputs gathered in the field to the least squares methods used to solve for the coordinates, all the way to the final adjusted positions and the precision measures that tells us just how much we can trust our results. So by the end of this report, you won't just understand what geodetic adjustment is. You'll understand why it matters and how it's done. So let's begin. So now I'm giving the floor to the next reporter.
Okay, so thank you, Carl. Now we will discuss the purpose of 3D geodetic network adjustments. But first, let us learn what a 3D geodetic network is. A 3D geodetic network is a system of connected survey points whose positions are measured in 3 dimensions: the x coordinates, the y coordinate, and the z or elevation coordinate. In surveying and geodesy, measurements are never perfectly accurate because errors always exist. These errors may be a result of human limitations, instrument limitations, natural conditions, and random errors. And because these errors are unavoidable, the measured data will not perfectly agree with each other. Thus, the main purpose of network adjustment. 3D geodetic network adjustments combines all observations into a single solution, reduces inconsistencies between measurements, produces the best fit coordinates using statistical methods, ensures the network satisfies geometric and physical constraints. So, this process improves accuracy, consistency, and the reliability of survey results. So without adjustment, survey measurements may contain inconsistencies that could affect engineering and mapping projects. So that's all for me. So I will be passing the floor to the next reporter. Thank you.
So, for the inputs and outputs of the adjustment, next slide please. In surveying, the adjustment process starts with several important inputs. These include observations such as distances, angles, both horizontal and vertical, and GNSS baseline vectors, which provide the raw measurement data. We also use initial approximate coordinates of the points as a starting reference, weights or accuracies to show how reliable each observation is, and control points with known coordinates to anchor the network. The purpose of these inputs is to define the problem clearly and provide the foundation for the adjustment. Once these inputs are processed, the adjustment produces outputs that refine and improve the data. These outputs include adjusted coordinates in x, y, and z. Next slide, please. Which are the corrected positions of points, residuals that show the corrections applied to the original measurements, and precision measures such as standard deviations and the variance covariance matrix to quantify accuracy. We also get quality indicators like error ellipses and network reliability, which also help us evaluate how trustworthy the results are. The purpose of these outputs is to confirm whether the adjustment succeeded and to demonstrate accuracy and reliability of the final survey results. Altogether, the inputs provide the raw data and references, while the outputs give us corrected coordinates, measures of precision, and indicators of quality. This ensures that our survey results are consistent, accurate, and dependable for engineering and mapping projects. So that's all for my part about the inputs and outputs of the adjustment.
So, what type of least squares observation equation applies here? So, next slide, please. So, it is indirect observation method. It is also called parametric least squares. So, why indirect? It is because we do not directly measure coordinates, but instead, we measure related quantities, distances, angles, azimuth, which are the functions of the unknown coordinates. So we need to work backwards. Next slide. So there are general form of the equation, which is the V is equals to AX minus L, where V is the residuals or correction to the observations, and A is the design matrix, which relates each observation to the unknown parameters, and X is the unknown parameters, which are the corrections to the coordinates, while the L is the misclosure vector, which is the difference of observed value minus the computed value using the approximate coordinates as shown sa lecture 13, and each type of observation has its own linearized observation equation, like for slant distance, for azimuth, for zenith angles, and horizontal angles, and each of them have corresponding coefficients. So all those equations, distances, angles, azimuth, or the elevation difference, they all get assembled into one big system of equation, and we solve them simultaneously using the least squares. That's all for my part.
So, good day everyone. So, I will be presenting the general workflow for adjustment of 3D geodetic networks. So, this process is essential in geodetic engineering to ensure that measurements are accurate, consistent, and reliable. So, first, in geodetic survey, raw field measurements often contain errors due to instruments in environment and human factors. To address this, we apply systematic adjustment process using mathematical methods, particularly at least square methods. This ensures that the final coordinates are most probable values. So we have 7 steps in this. So step 1 is data collection. Our first step is the data collection. In this stage, we gather all fields observations such as distance, angles, and GNSS data. These measurements serve as a foundation of the entire adjustments process, so accuracy and completeness are critical. Next step is initial approximation. Here we assign approximate coordinates to unknown points. This step is necessary because it's the mathematical equations we are nonlinear and we need starting values to begin the computation. Next, step 3. In model formulation, we develop observation equations to relate the measured data to the unknown coordinates. Since these equations are nonlinear, we linearize them using Taylor series expansions to make them suitable for computation. Then, the step 4 is to set up least square system. So we constructed the least square system we form in design matrix, denote as A, and observation vector, denote as I. If needed, we also apply weights to reflect the reliability of each observation. So the next step is solve the system. To solve the system, we use the least square formula to compute corrections to the coordinates, which is x is equal to ATPA to the power of negative 1 ATPL. So this equation allows us to determine the most probable correction by minimizing the sum of squared errors. So we have the step, we will proceed to step 6. So compute residuals. After solving, we compute the residuals by representing the differences between observed and adjusted values. They help us understand how much each observation was corrected during the adjustment process. Then, step 7, accuracy assessment. In accuracy assessment, we evaluate the quality of the results. We compute statistical measures such as standard deviation and other covariance matrix. These indicators help us determine whether the adjusted network meets acceptable accuracy standards. So last and final step is final coordinates. So finally, we compute the final coordinates by applying the corrections to the initial approximations. So these adjustment positions represents the most reliable and consistent values of geodetic network. So that's for my presentation. Thank you for listening.
So hello everyone. So to bring our presentation to a close, let's take one last look at the big picture we've covered today. We've walked through the entire life cycle of 3D geodetic network adjustment. It's easy to get lost in a matrices and Taylor series, but remember the core mission. We're taking raw, imperfect observation from field, our distance, our angles, and our GNSS vectors, and we are subjecting them to the ultimate mathematical standard. By using the indirect observation method, we aren't just calculating numbers. We're solving a puzzle where every piece has to fit perfectly. We move from our initial approximations through the engine of the last least square system, and finally into the crucial accuracy assessment. So why does this matter? Because in our field, close enough doesn't exist. Whether we are checking for the reliability through error ellipsis or calculating those final XYZ coordinates, we're ensuring that the infrastructure of tomorrow is built on the foundation of a mathematical truth. It's been a deep dive into some heavy lifting, but that is what defines us as geodetic engineers, the ability to turn mountain of data into a single perfect solution. As the final speaker of Group 4, I would like to thank all of your attention and for following along with our lecture. We've enjoyed breaking this down for you. That officially wraps up our report. Stay precise, keep adjusting, and have a great rest of your day. Thank you and goodbye.